Okay, go ahead.
Welcome to the TUM AI lecture series. My name is Daniel Kremers, and it's my pleasure to introduce today's speaker. Today we have Andrea Vedaldi with us. He's professor of computer vision and machine learning at the University of Oxford, and he's co-leader of the visual geometry group. We actually go back a long time. I remember meeting him for the first time 15 years ago when he started as a young PhD student at UCLA. And he's had a stellar success ever since and has moved up the ranks and has published hundreds of papers in machine learning, artificial intelligence, and computer vision. He's also very known for open sourcing a lot of code. In particular, VLFeet and MatConfNet have been extremely popular. And today he will speak about learning representations and geometry from unlabeled videos. Andrea, the floor is yours.
All right, thank you, Daniel. I hope we will not have more technical issues down the line. It's true, we go back a long time, actually more than I care to think about, I guess. But yeah, that's life, I suppose. So, but today, as Daniel was saying, I would like to tell you about some of the work we have done in terms of learning from videos. Unlabeled videos, in fact, and what videos can tell us about image representations as well as geometry. Okay, but before I dive in, I would like to give you maybe a little bit of motivation of why this may be an interesting problem to look at. So I think the starting point is really to think about how your work can have an impact on people. So presumably you're all researchers in machine learning, computer vision, and so you create stuff that eventually is going to get into the hands of people. And how is that going to happen in practice? Well, I think there are two main ways this is happening today, or should happen at least. So the first is addressing what they call horizontal problems. So an horizontal problem is something like autonomous driving, social networks, internet search, medical imaging, where you create a sort of application which is based on machine learning, and then that's delivered identically to a very large group of people, maybe millions of people, maybe even billions. Okay, so this is why this is horizontal. It has a large impact because you're serving a lot of people. But then there is another class of applications that you could call vertical problems, which are much, much narrower. So these are of interest to a very small group of people. Maybe it's just an individual user, but it can have a very big impact specifically to that group of that user. Okay, so what are examples of that? Well, for instance, if you look at the humanities, so here's a picture of, actually this is a real thing. So this is how a bibliographer would actually compare ancient manuscript to search for correspondences. Now, this is obviously something that you can automatize using computer vision or using machine learning. And if you can provide an AI that a person like that can use, then it can multiply manifolds the sort of analysis that it can run. So it can effectively transform the field. All right, so it's a very specialized use, but it can be transformative for the entire research field. And this is similar also for something like archaeology, or maybe if you study fine art. So these are all applications which a computational approach does not exist yet, or not in a significant manner. But that is where you could have really have an impact of sort of this vertical nature. But that is not just humanities. If you go and talk to a zoologist, for instance, here you see an application that we have built that is able to count penguins in these regions. So each region here is a nest, and we want to know how many penguins are there in each frame of the video, and use that to build a statistic. And this is useful for zoologists because they can use that to measure the health of a population of penguins, or a group of penguins in Antarctica. And if they do that for long enough, then you can also have an idea of the effect, for example, of climate change on these penguins. And if you don't have AI, you need to have a grad student actually does the counting. So you can see that AI can really multiply the sort of size of data you can process, and also the quality and the systematic nature of the analysis, if you like. Here's another example. So these are crystals that are forming as a metal is cooling down, and you want to count them. And that's important to material scientists. So this is another example in which, if you did have an AI, and it is possible to build it, then you could actually have a very big impact on this kind of research. All right. So there are the huge variety of specialized application of vision or computer or machine learning that we would like to serve. And we can, in theory, because the technology is there. So these are examples that are actually successful. But in fact, most of these applications are not addressed. And the reason is that machines are not flexible enough. So if you are a scientist, you want to use computer vision for solving a problem, but you're not an expert in computer vision, then you need to find an expert, and that expert will have to provide the technology, the expertise, as well as the data to train the machine from, right? So data means big data sets usually. So we know that big networks, they're trained on something like ImageNet, open images, et cetera, et cetera. So we're talking about hundreds of thousands of millions of images. But the issue is not really that one. So the issue is that these machines are supervised. So in addition to having the images themselves, that's maybe sometimes you can get for cheap from the internet, you also need to label them. And depending on the nature of the labeling, that can actually be very expensive. So you see here an example of images that have been annotated for segmentation. And so each individual pixel has been marked with a semantic label or name. And as you can imagine, this process of semantically annotating an image pixel by pixel is very expensive. And if you want to do that for hundreds of thousands of millions of images, well, this is not something that a common human, if you like, is able to do. You need experts and you need resources to do it. So what's the solution there? Well, there are many things you need to do before you can address all this myriad of potential application of vision, but one of them is certainly remove the need for supervision. So this is what we're going to talk about today. So how can we train machines, maybe on the assumption that we have the images and the videos, but we don't really have the supervision. So how can we get rid of that? And one way is to use self-supervision, which means seeking some sort of supervisory signal in the data itself. So I'm going to discuss several things you can learn in an unsupervised manner, and I'm going to start from representations, because that's the most low-level and potentially more flexible thing that you can do. All right. So what is a representation? So representation for me is just a function I'm going to call phi that takes as input a tensor, which is usually an image x, and produces as output a vector, which is an element in some Euclidean space, which has d dimensions. And of course, what we're going to do to implement this function is to use a deep neural network. For example, you see here a schematic representation of AlexNet, but that could be any neural network really. And so I'm going to look at that as the viewpoint of a map that takes your input image or video and maps that into a vector. Now that vector we call a representation of the image. And why is that interesting or useful? Well, because usually, or always really, you have another bit of a machine, which is a classifier, a predictor, that takes that vector and maps that onto a name or a label or some information which can be useful for a human. In this case, is the name of the class which is contained in the image. So goldfinch is a breed of bird, right? So this last step here converts this representation into some information which is useful for an application, something that can be interpreted by a human. So the goal of machine learning is, of course, to learn, in addition to the classifier, also the representation itself. But so what's the nature of what should the representation actually do for us? Well, the story here is a little bit simplified. So there is a lot more nuance of what I'm going to say right now. But as a first approximation, you can think that the goal of this representation function is to take a notional semantic similarity between data points and map that into a notion of vector similarity at distance. So just to illustrate that a little bit more clearly, so suppose we have these three images. So we have X, Y, and Z, all right? Now, the first two are congruous in the sense that they contain the same object. They're both bicycles. And the second two, Y and Z, they are incongruous because they do contain different objects, like a bicycle and a dog. So we would like to get a representation which maps those images onto vectors in such a way that if the images are X and Y, so they mean the same, then the vectors are close. And if the images are far away, the images mean something different, then the vectors are far away. So we want this representation to be invariant to what we call nuisance factors, for example, changing the viewpoint or changing the particular make of the bike. But we want the function to be sensitive to changing the meaning of the images. So going from a bicycle to a dog, then we want the output of the function to change a lot. Okay, so that's what the representation should be. Should be a function which is invariant to nuisance factors and sensitive to semantic factors. Now, the standard way, the standard approach would be to train this function using some supervision. For example, knowing beforehand that these two images contain bicycles. But suppose you do not know that. So what do you do then? Suppose you only have images. Well, so one thing you can try to do is to find a proxy to this task of learning a representation which is invariant and sensitive. And what we're going to do is, instead of considering the image X and Y, which mean the same because we have labeled that, you're going to replace y with the t of x. All right. So t of x is simply a transformation of the image x, which is meaning preserving. For example, if you flip the image left to right, then that's still a bicycle. So that's a transformation which is typically, usually meaning preserving. So we can use it to get a pseudo image y here, which is really a derivation of the first. But at least we know it's not the same image, but it has the same meaning. Okay. And we can also generate an incongruous pair of images, tx and z, by simply sampling another image at random from a large enough data set. Now we're going to make a bet that if we do this at random, then the image that we're going to pick here, most of the times, is actually going to contain a different object. So now we have created a triplet of images, x, tx, and z, where the first two are congruous, so you want the representation to be near, and the second two are incongruous, so we want that to be far apart, all right? And we can use this as the basis of setting up a learning problem that does not require supervision, because all we need here are a bunch of images and the ability of synthesizing or sampling transformations, okay? So this is, of course, at the basis of what is known as contrastive learning, which is now a popular way of learning representations. So this usually works by picking a data source. This could be some data set of images downloaded at random from the internet. Then you form a batch of images. So that means you sample any images from the data source like that. And then for each one of those, you sample two transformations. So you get two versions of the same image that differ from, because, for example, the image has been rotated. And then you have a representation function that maps those transformed images into a representation space, an Euclidean space, which is now represented by a sphere. And what you try to do is to learn phi, your neural network, in such a way that if two images come from the same one transformed in two different ways, then you sort of pull apart the representations like that. But if they are images that are sampled from, obtained from different samples, then you push them or push their representations far away. Okay, that's the basic, in a nutshell, what Simplier, Moco, Suave, and all these methods actually do. All right. So which kind of representation can you use here? Well, if you have an image, you can do stuff like cropping the image, occluding part of it, rotating it, maybe moving the color, etc., etc., etc. All right. But suppose now we actually have videos. So videos are a lot richer than images. So maybe there are more opportunities to set up contrastive learning formulations with them. And in fact, this is actually true. So for instance, here you have two videos. And so if I play them, well, is it actually playing? Yes. Okay, so you see that there's a guy that is playing the drum and another guy which is playing the guitar, but you don't hear anything yet, all right? So now in this case, what I have done is selecting only the visual modality. I throw away the audio. And now what we can do is we can listen to the audio instead. So I'm gonna play the first track and then the second. Okay, so that was the first track. And that's the second. Now, of course, if you hear them and you listen to them as a human, you immediately know that actually this is wrong. So this track should go here and this track should go there, right? So you can contrast what you see with what you hear. And now this is also a basis for setting up a contrastive learning problem, all right? So you can use modalities as another way of generating a contrast between information or views of the same information so that you can get a supervised signal from, all right? There's one more thing though. So if I give you a transformation of data, so in this case, this is a video, and what I applied here is time reversal. So I swapped the axis of time. Then you might wonder whether you should be learning a representation function that is invariant to this effect, or should actually be sensitive to that effect. This is not obvious, right? So if you rotate an image, then yes, that's something that most application you would like to be invariant to, because you want to recognize the object regardless of the rotation. But if you reverse the sense of an action, it's not clear whether you should be sensitive to that effect or insensitive or invariant to that. So we can also play with whether we want to be distinctive or sensitive or invariant to transformations. So in this work, which is called Generalized Data Transformations, what we have done was exactly that. So we have taken all these possible effects, we have systematically explored them and reduced them to applying certain transformation to your data set in such a way where we can explore different kind of effects we can apply to videos, as well as the interplay between distinctiveness and invariance. So to give you a concrete example, we start from a video collection. Then the first kind of transformation that we use are applied to the collection itself. So the data set is where we apply the first kind of transformation. And the first transformation kind, in this case, is simply data sampling. All right, so we select certain number of videos at random from our data sets, just as we were selecting images before. But then what we do is we apply different kind of transformation that makes sense for videos. So we apply time shift, so we get two versions of the same video clip with different, maybe a bit earlier, a bit later in the stream. And then for each one of those, we slice modalities. So separating the visual part from the audio part, we also look at that as a transformation of your data. And then eventually we apply augmentations. For example, we can rotate an image or maybe suppress some Fourier frequencies in the audio. All right. Now you can see that from top to bottom, we get sort of a branching set of transformations that we can sample. And eventually we can decide whether any pair of such data points should be, the representation of that should be pulled together or pushed apart, depending on whether we want to be invariant or sensitive at different levels of the tree. Okay, and then we can try all these combinations and see what is best. So if you do that, you discover immediately that, first of all, it's not obvious that you should always be invariant. So here is, so to explain this experiment, what we have done was to train our representation using contrastive learning. And we were trying to be either invariant or distinctive to time shift in this case. Then we trained the representation and we applied on a data set which is called HMDB51, which is a data set where the goal is to classify videos. And we fine-tune the representation there and see what is the accuracy. And you can see that if you are distinctive, that is to say sensitive to time shift, you actually perform better than being sensitive to that or just ignoring transformation altogether. And the same is true for time reversal. Okay, so these are two examples in which you can use these transformations, but it's better to be distinctive as opposed to insensitive to them. And if you combine these two things together, you can get even better performance. So when we introduced that at the time, so this was either significantly better or on par with state of the art. And if you're interested, you can refer to the paper to see a lot more experiments. But this is basically working well. And it's interesting because it allows you to explore these spatial combinations in a systematic manner. And there are really, really many of them, even things that we didn't have the time to test just yet. Okay, so that's about generalized transformations, but let's go back to this problem of learning from videos. So now we're gonna shift the problem slightly. So instead of separating a video in terms of a visual component, audio component, I'm going to consider a second modality, captions. So I'm gonna assume that videos comes with captions, and I'm gonna treat that as a second modality, right? So you can do that, and then you can use the framework we have just discussed to learn from these videos. And if you do that, what is going to happen? Well, first of all, you're going to have a bunch of videos with their captions, and you're going to try to pull those representations together. And then you're going to start to compare different modalities across different samples. So you're going to compare the caption of the first video with the visual component of the second video, and you're going to try to push them apart, right? This is what the recipe tells us to do. But does that make sense? Well, it does, provided that the videos have a different meaning. But as it happens, sometimes you do sample two different videos from your data set, and they happen to be video that contain the same subject. So in this case, a person throwing a ball. Now, this is a limitation of contrastive learning, which assumes that a priori, if you sample two different images of different videos, their meaning is going to be different. But this is actually not true in general. So sometimes you're not lucky. You take different videos that actually mean the same, and you push apart the corresponding representation, and that's a mistake. So what we did here was to try to, and by the way, there are many ways in which you can push things apart because all the combinations are valid, okay? So there's a lot of, so the learning framework is gonna put a lot of effort in trying to push apart things that actually should go together. So to try to sort of somehow reverse that, or at least compensate for that, what we did was to try to come up with a different learning signal that is better at picking out when things actually should go together. And so to do that, what we did was to assume that if your batch is large enough, for every video you sample, there's going to be at least one more video, perhaps more than one, that actually relevant to this one. And so in order to discover that, what we do is we learn the representation in such a way that is going to form an attention that tells us that these two videos are relevant to this one we want to describe. And condition on this attention, we combine the representation in a sort of mixed embedding, and we condition on that to generate the caption of the first video, okay? So this we call cross-captioning. Basically, it means that within a batch for each video, we seek for all the videos which are relevant to that, where relevance is defined as if you look at those videos, then we can predict the caption of the first video back, okay? And that, I know this sounds a little bit contrived, that actually works well, and this will try to pull together videos that are related because they're sort of interchangeable from the viewpoint of captioning. And if you do this, you see that this is another kind of evaluation. This is done on text to video retrieval. And this is a retrieval at 1 and retrieval at 5. So it's almost like top 1 classification error and top 5 classification error, but for retrieval. And you see that if you don't use or you do use this sort of cross-captioning, regularization, if you like, then you actually do get an improvement, which is 2 or 3 percentage points consistently, which is actually not an easy thing to get because this data set, they tend to be saturated. So it's actually, although I know that if you look at the graph, the difference seems like a little bit small. Actually, it's non-trivial to get that. And there's also a question of which is the batch size that you should pick, because the fact that you're going to find a video or not which is relevant to the one you choose, well, is only possible if the batch size is large enough. But if a batch is too large, then the constraint you're going to impose is actually going to be rather weak. So this is somehow a sweet spot that tells you that if the batch size is just right, then the regulation strength is going to be optimal for you to learn a representation which is as good as possible for retrieval. Okay. All right. Now, that was the first part of the talk. In the second part of the talk, I would like to gradually move some levels up in terms of what we can discover from videos. So far, I discussed learning representations. Representation means that we learn these vectors here that we feed into a classifier or a predictor to get something which is interpretable to a human. Okay, but the point is that representation itself, the vector, does not mean anything to you. So this is only useful if you have the ability of turning that into a predictor, or feeding that into a predictor that usually requires a form of supervision to be trained. All right. So per se, the unsupervised learning step does not produce anything which is useful to a human. You always need a little bit of supervision to then convert that into a usable signal. Now, what I want to do is to try to instead learn directly the entire thing, therefore to get an output which is directly interpretable to a person. Okay, so that's going to be the goal of the next part of the last part of the talk. So the first thing I'm going to consider is, well, maybe the easiest such examples, which is clustering. So what we want to come up with is, in fact, the cluster the image automatically, and you could cast that intuitively as clustering the representation vectors. So you get your AlexNet or your ResNet to produce vectors, and then you look at them as points in some high-dimensional vector space, and maybe you just run k-means to partition that space into Voronoi cells or clusters, and you say that each one of those clusters then has a meaning. You hope that it has a meaning. You need to verify it a posteriori, but the goal is that those clusters should be as human-aligned as possible, if you like. And now, if you just apply k-means here, what happens is that you can define an energy function like that, which says, the way k-means is defined is by throwing some means into the mix. So each one of these ball is a mean vector. And then the Voronoi cell is defined as a set of points which is closest to the corresponding mean. And to train k-means, you'll optimize this objective function here, which says that you're going to arrange those means in such a way that the average distance, so the average minimum distance to the data point is minimized. Okay, and that's going to adjust your means and give you, well, quote unquote, optimal clusters. But what we want to do here is more than that, but because what we want to do is to learn simultaneously the means as well as the representation itself. So we want to learn phi and we want to learn mu's. So if you do that, what happens? Well, if you just naively minimize that, what happens is that you map everything to the same mean, and then you tweak your representation to be a constant vector, which is equal to the mean. And this works because you have the freedom of choosing the means as well as phi. So it's completely trivial to satisfy the k-means criterion in this manner. So this is not very interesting, all right? So what we did then was to try to find constraints, or additional constraints, which would allow you to find non-trivial solution to clustering, even if you train the representation together with the clustering function of the means. All right, so this is what Sela or self-labeling actually is. So it combines two ideas. The first one is that your clusters should be transformation invariant, that is similar to what we have done for contrastive learning. And two, what you want is that the cluster have equal mass. Now that's a strong assumption that we can relax, but for now, that's what we're going to do. And this is key because that is exactly what you need in order to guarantee that those clusters do not collapse. Okay. So formally, this is what this looks like. So we have, a sort of EM-like or alternate optimization approach, in which we have a network that takes an image and maps that to a class name or the class index, if you like. So that's just a classifier. And then we have a label assignment table, which is just a probability table that assigns each image index to the corresponding class index. All right. And we want to learn these two things simultaneously. So to do that, if you fix Q, that gives you basically the label for each image. Learning your network comes down, reduces to just a cross-entry minimization, which is what you do when you train a network for ImageNet classification, for example. So just completely standard. So this sense of the error is standard. And that allows you to train fine. So these classes are transformation invariant though. So you need to apply random transformation to your data point when you run this optimization. But that's also standard because that's the same as data augmentation when you train a network for classification, say using ImageNet labels. So this part is fine. Going the other way around though, amounts to optimizing the same energy function with respect to Q under the constraint that if you sum this matrix along the rows, then you get a vector of identical numbers because you want your classes to have equal masses. Okay, and if you do that, you discover that this is actually an optimal transport problem that you need to solve on a very large scale. So I have millions of images and typically thousands, not dozens of thousands of classes. And if you use linear programming, that's just it's not going to do it for you. But fortunately, there are very fast solvers for optimal transport. We use here the synchron algorithm. Actually, that's a very elegant and nice thing to know about. So if you don't know about it already, I suggest you to look at the paper and then the literature to learn more about that. But it's basically something very simple that with a few matrix calculations, it can give you an optimal solution to this transport problem, and therefore the optimal assignment under this sort of equipartitioning constraint. Now, but what I want to do is not to work with images, although we did that in the past. What I want to do is to work with videos. So what we did here was to transform our formulation in such a way that we would actually get two clustering functions, one that's the clustering based on the visual components of your video, and the other one that does the same but from the audio components. Okay, so we have phi A of audio, so that's the network that gives you the representation of your data from the audio track, and then phi B of video. Actually, I should say probably visual here. That does the same for the visual component of your video. Okay, and the key here is that you want these two clustering functions to be consistent, so to produce the same labeling effect regardless of which modality you're looking at. So we measured this in VGG Sound, which is a recently introduced data set of videos that have labeled that are being determined by humans, and these are semantic labels. And then the goal here is to see whether we can get synthetic labels which are close enough to the semantic ones that we get from people. And to measure that, we use NMI, which stands for Normalized Mutual Information. It's just a measure of alignment between two clusterings of a data set. And you see here what happens if you only use visual information, or if you use this idea of getting this sort of modality consistent clusterings. All right. And you see that the difference is dramatic. So it is more than that. The performance is more than double. All right. Now, why is this so? Well, the intuition, I believe, is that if you think about it, videos, so they have a visual and audio parts, and the only relationship that exists between these two kinds of signals is really the nature of the object which is contained in the video, for example, a guitar, right? Because that has a characteristic appearance that goes with a characteristic sound. So if you look at this contrast, then you really do get a proxy for the semantic cluster or the nature of the object which is contained in the video. Okay, and this shows that in fact it works very well. And if you compare that to, say, using Moco or Simplier or something like that, and just clustering the output of that with k-means, actually this actually works better. Okay, so it's not just a fluke. It really does help to do this sort of to consider clustering together with representational learning as opposed to just do representational learning directly. Now here's the demo. I wanted to show you a few clusters. I am afraid that if you're gonna leave the presentation, then this is gonna crash and I will not be able to present anymore. So unfortunately, I'm gonna skip the demo. You can check this out online and you can see some of the clusters that are found. I think it's fun to look at them. They usually look quite nice, actually. So I invite you to have a look if you're interested. Maybe gonna come back to this later if there is time, and after I can, sort of sacrifice the rest of the presentation. Now, what I would like to do in the remaining 20 minutes or so is to discuss more meaning or different kinds of meaning that I hope we can extract from data and from videos without using supervision. And what I want to focus on is geometry. In fact, this, you can argue, is going to be probably the focus of my research for the next 2 or 3 years, I think. So extracting geometric information from images and videos without supervision, okay? Now, this is the study similar to the one I just said you about clustering. So what I want to do is not just to train a representation, but I want to train the network to produce information which is interpretable. But now that information is going to be in the form of geometry, right? Geometry is interpretable to a human because we understand it. We can even formulate it analytically. But I think there is an advantage here. So geometry is also like physics and dynamics is low level. So it has an existence which is to an extent is intrinsic in nature. I don't know whether philosophically this is a correct statement to make, all right? But I think it's fair to say that geometry is much lower level. So it does not depend on human construct like culture, what is beautiful, or categories like this is a phone and this is a keyboard. It's much more down to the metal, if you like. And therefore, because it does not depend so much on human intuition or human culture, I think this is something that networks can learn or machines can learn much more automatically without us having to tell them anything, okay? So this, I think, is a very good starting point for unsupervised learning. Okay, that's the philosophy, but what have we done about that? Well, I'm going to tell you mostly about 2 or 3 works here very quickly. So the first one is 2D geometry. So suppose you have a video of a person which is running and you want to learn about key points or maybe the shape of the body, but in 2D. So you want maybe to approximate that with a stick figure and you want to do that automatically. What can you do? Well, one approach is to use autoencoding. So what this means is that you're going to take your input image or the input video, you're going to encode it with a network into some geometric code, and then you're going to use that to generate the image back. Okay. So, and this is the basic idea. So now you can close this into a reconstruction loop, which means that you train your encoder network and your decoder network in such a way that the reconstruction is as faithful as possible to your input. Now, this can work, and this is just an autoencoder, but does this really learn geometry? Well, yes and no. Yes, if you actually change this a little bit. So what are the changes that you require? Well, first of all, we need something that encourages this representation of geometry to be meaningful, to in fact encode for geometry. So one thing you could do, for example, is to make the code into the shape of a bunch of landmarks. So maybe represented with their 2D coordinates. So you shape the code analytically in such a way that that's a clear proxy to geometry, right? Maybe you can also design the network here to have a direct inductive biases, but mostly you shape the code in such a way that you can interpret that as a human as a bunch of key points, okay? So that's the first step. But suppose you are successful and you can in this way isolate geometry only. So you can squeeze out everything else and get the network, the encoder, to only put the geometry here. Now you immediately realize that there's a problem, and the problem is that from geometry alone, just a stick figure, you cannot reconstruct your human anymore because you lack fundamental information. For example, the color of the clothes, so maybe what is the texture of the background. So in order to make this solvable, well, what you need to do is to use instead conditional autoencoding. So I think this is a super useful idea that works particularly well for videos. So what we do here is we take another frame of the video. And the assumption there is that the appearance of the object in the second frame is more or less the same as the appearance of the objects in the first frame. And that's usually true because the person is not going to change his clothes mid-run, right? And then what we do is we condition the decoder to use the geometric information that is extracted from the first frame, the appearance information, which is extracted from the second frame. And now the goal is to reconstruct the first frame for which the decoder only sees the geometry, okay? Now, why does this work well? Because if you think about it, the appearance is the same, but the only thing that really changes between the frames, or the main thing that changes between the frame are the geometric parameters. In this case, is the pose of the person, okay? And therefore, by looking at what changes in the video, that's a very strong proxy to geometric effects or changing parameters in the geometry, okay? And that's why this pulls them out very, very happily. Now, the actual implementation of this is quite a bit more sophisticated. For example, instead of extracting a set of key points here, we actually do literally map an image of a person to an image of a stick figure. And we have a discriminator network that guarantees that this guy looks like a stick figure. And I know this sounds crazy, but there are reasons why you want to do that. The primary reason is that learning a network that converts an image into another image, as opposed to an image into a set of key points, is actually easier because you can use what are known as image-to-image networks, or for example, what is used for image segmentation, and they're easier to learn. So it's actually an easier problem to set it up in this way, although on paper it looks a lot more complicated. So again, if you're interested about the details, please have a look at the paper. And there are quite a few more interesting things that I don't have time to discuss now that go into making this work, which I think go beyond this particular work as well. So it's useful to know about that. So just want to show a bunch of results here. So you see here a landmark detector. So this one has been trained by having sort of prior what a human face looks like in the sense of, the landmarks, they tend to follow this particular pattern, but the detector itself has never seen any image or video frame which has been annotated with landmarks. So the way the landmarks have to be aligned to a video, that's learned completely automatically without any annotation whatsoever, okay? So that's non-trivial. And you can see that then you can take these landmarks and you can move them by hand and check out the effect. The generated image is actually what we would expect based on the geometry that intuitively has been captured by those landmarks, okay? And it also works if you want to parse humans. So here you see the application of Human 3.6m, pen actions. So these are relatively simple scenes. So, and human detection has much greater performance if you do it supervised. But this still already see that these methods can start to align these geometric primitives to videos without having to provide supervision for it. Okay, so the last part of the talk, I'd like to discuss 3D information, and I'm going to discuss two things in particular. But just to motivate them, you probably know that now we have machines that can do 3D parsing of humans very well. And now this is fine, but those machines are learned with a great deal of effort. So typically you need complex hardware like DOMs to create a data set of 3D humans. And with those, then you can train very good networks that can lift, say, 2D images or videos into 3D. For example, this one, which is, this one here, whoops. This is a model that we did learn in Facebook. And so this is a network that's been trained using supervision, okay? And there is a difference between the top and the bottom one. I don't want to discuss it, but just suffice to say that ours is the bottom one, which performs a bit better. But what the purpose of this is to show you that now you can take very complex scenes, even with heavy occlusions, and somehow this network can figure out how to attach sort of 3D shape to those images and videos, okay? This is actually pretty challenging. And of course, this is not, there are plenty of groups that can solve this problem very well. But, so that is possible because you have the supervision. But what if you want to now learn about, say, elephants or Coke cans or, potted flowers and all the rest which exists in nature? Well, it's not possible to repeat this pipeline for all these objects. It's just too expensive. So you cannot put in your DOM an elephant, all right? So what we need to do is to be able to learn 3D information from either no annotations or at least weaker annotations. So in C3PO, this is exactly what we did. So this is a no-rigid structure for motion model, which is based on deep learning. And so what this takes as input is a key point detector, which has been manually trained. And then there is a model that is trying to explain that, to lift that to 3D. So the way this works is you take those 2D points, extracted by a detector which has been pre-trained. And then you have a network that you're learning, phi, which maps that onto alpha, which is a set of coefficients that you use for basic functions whose purpose is to reconstruct the 3D configuration of those points in a sort of object-centric manner. And then you also learn a function that produces RNT, which are the rotation and translation, which give you the viewpoint of that object. And then given the 3D reconstruction and the camera, you can reconstruct back to the points you observe in the image. Because this is similar to autoencoding, if you like. You close that into a loop, you have some other tricks that are explained in the paper, okay, which are maybe not completely trivial, but then if you do that well, then you can learn effectively to lift those 2D points into 3D space, okay? And so what is the good thing about this representation? Well, it does 3D reconstruction, it captures intra-class correspondences because these key points are the same for all kinds of birds, for instance. So it gives you an explanation of an object categories as opposed to a single instance or scene. And then it also gives you the reconstruction, which is canonical, because the reconstruction is from the viewpoint of the object, not the viewpoint of the image. So it really explains the object and the object category as opposed to explaining just the image. The limitations, of course, is that it requires a key point detector and is a sparse reconstruction. These are some results of C3PO on reconstructing birds and some other examples of that reconstructing other object categories like plane, cars, motor bicycles, and another plane. Okay. So it works well, but has these limitations. So suppose you want to go beyond that. So we can consider other kinds of representations for the information that we might want to use. One is depth maps. So a depth map simply is a function that, given an input image there, For each pixel, it tells you how far away that pixel is from the observer. Now, what is good about that is that that's a 3D reconstruction of sorts, right? It tells you, the shape of the scene, and is a dense reconstruction. It's not sparse, and this does not require a key point detector. That's just a network that is trained to produce this depth knot from a single image, say. But the limitation here is that it does not really explain a category. It's not object-centric, it's view-centric, and it does not give you correspondences. So if you see a different image of a bird, well, that knot is not going to tell you how things match up. If you really want to get correspondences, which is key to explain a category, so what you need to do then is to use some other mechanisms that can tell you about them. And so what you can compute, for example, is canonical map. This is something that has been done forever, actually. And it seems to be rediscovered every couple of years. This is what is done, for example, in DensePose. But the idea here is that you learn a network that for each pixel in your image, like Y here, maps that into kappa. Kappa is just an index of the corresponding object point, where you abstracted away the actual shape of the object. So this sphere here is supposed to be topologically equivalent to the surface that defines the bird. And each point on the sphere, the goal of that is just to put a name to that particular point. So you can imagine that the given value of kappa represents the left eye, and another value of kappa represents the right eye, okay? That is what a canonical map actually is. And in order to explain that even further, if you see point Y and Y prime in two images, two different birds, and they happen to be the same point semantically, then these functions, these canonical maps, should map both of them to the same value of kappa, okay? Now, the advantage of that is that it's dense. It does capture intra-class correspondences by definition, but it does not do any 3D reconstruction because all you get is a sphere, all right? So we have these three guys. What are we going to do next? Well, you guessed it. We're going to try to put them together, all right? So this is what we did in Nurich this year. So this is called canonical 3D deformer maps, C3DN for short. So this is very similar to the model we use for non-rigid structure for motion, except that now these basis functions are not sparse, they are dense. And this is possible because we are combining them with a canonical map that for each pixel tells us which landmark or which point on the surface we're looking at. And then there is another function B that is also implemented by the deep neural network. So is a continuous function which is learnable. And that function tells you what is the 3D point that corresponds to this particular value of kappa for the different shapes that you get in your basis set, okay? Okay, that's what the model is. And this does not require a key point detector because the key point detector effectively is implicit in the canonical map itself. So you don't need that as an external mechanism anymore, okay? If you do that, these are sort of things you can learn. So you can learn 3D reconstruction of birds, which look pretty reasonable. And you can look at cars. So there are many other works that are concurrent to ours, which obtain similar or perhaps even better results. Still, I think this is a very interesting model because it's a direct generalization of rigid structure for motion, okay? And because now you know the correspondences and the shape of different objects, you can do things like texture transfer or reenactment, which means you can take the shape of this bird, the texture of that bird, and get a combination of the two, right? That's because the model understands these factors explicitly. Okay, now, final thing I want to discuss is this. All right, so far we have seen a method that can learn about 3D shape, but they all need a little bit of supervision. Either, well, generally speaking, if you look at literature, either you have a prior on the 3D shape of, say, a person or a face or the object you want to reconstruct, or you have multiple views, maybe you have RGBD data, maybe you have silhouettes, maybe you have information about the key points, maybe you have the camera viewpoint. So if you look at carefully at papers that came out until at least last year, well, they all use one or two of these ingredients, at least one, right? What is really, really hard, we figured, is getting rid of all these things together, right? So if you don't have any of that information, can you still do the reconstruction? Well, this is what we did here. So the goal of this work was to take a collection of images. There is a little bit of supervision because we cropped them around the object, in this case, cat faces, or could be human faces. And the goal is to learn without any hints, without prior about 3D shape or viewpoints or multiple views or anything like that, to learn a function that can take one of those images at a time and reconstruct it in 3D, okay? So this is what we wanted to do. Now, again, so if you use more supervision, you can get better results. So if your goal is to get good 3D reconstruction of human faces, you should not be using this, you should be doing something else. But if your goal is to try to get rid of supervision, I think this is a interesting thing to read, okay? Now we're going to make one more assumption. So most objects in nature, like humans, animals, and most man-made objects, they are symmetric. They have a bilateral symmetry. So we're going to assume that in probability, our objects are going to be symmetric. And that's going to be useful for constraining the construction problem to some extent. Okay. And so then let's see how we've done this. So the basic idea is still to use a form of autoencoding. Okay. And we're going to use symmetry. And I think the reason why this works well is because of the basic setup as an autoencoder, but also because of a bunch of design choices we have made, which are maybe not so obvious when you read the paper at first, but actually very important to get good performance. So I'm going to try to explain them now. Okay. All right. So what's the story? So we take an input image I. So this is just sample at random in your data set. Then we have three networks here: one which estimates the viewpoints, one which estimates a depth map, and another one which estimates a texture. And then we have a function which is called a renderer here that takes these three ingredients and combines them to give you that image back, right? And this renderer is done analytically, is handcrafted, and this is what gives an interpretation or a meaning to the factor WD and the texture as what they are, right? So the reason why this is that map is because of the analytical choice we have made in the design of the renderer, all right? Now, you can try to just close this into a reconstruction loop by putting in a loss, a reconstruction loss like L2 loss, for example, and you can try to train that. So what do you think is going to happen if you do that? Well, intuitively, nothing's going to happen because the easiest solution for the autoencoder is just to say, okay, my depth is flat, the viewpoint is constant, and I simply get a texture which is a copy of the input. So if you do it, this is exactly what happens. So you don't get any 3D information, you get a trivial solution that's not interesting. So this is where we add a symmetry. So what we're going to do is we're going to assume, or we're going to force the texture to be symmetric as well as the depth map to be symmetric. And if you do this, then you're going to see that the reconstruction you get is not degenerate anymore. So you do get a 3D shape here, which is non-trivial. Again, this is the degenerate version. If you have symmetry, the degeneracy goes away, right? Now, here's the first trick. So how are you going to impose the symmetry? One thing you could do is to just use another loss function, take your reconstructed texture, you flip it, you compare it to what you got before flipping it, and you want the difference to be zero. Sure, you can do that, but that's annoying because that introduces another loss term. You have to choose a weighting factor for that. No, what we did was much was simpler in the sense of eventually learning the model. So what we did was introduce a flip switch here, which at random flips or not the corresponding data point, the corresponding information. So for example, if this is set to 1, instead of set to 0, then what flows into the render is not the depth map, but is the flip depth map, right? And if you think about it, if this is done randomly, then the easiest way for the network to make sense of that is to try to make these two bits of information symmetric, because then when you flip them, nothing changes, all right? And then the job of the renderer is much easier. And this is exactly what happens. So this is a trick in which you inject a perturbation in your data flow in such a way that you get to learn the desired invariance, okay? And so if you do that, in fact, you get a texture which is symmetric and a depth map which is symmetric without having to introduce loss terms. But if you think about it, this is actually too much of a simplification because although faces are structurally symmetric, there are many sources that make many factors or nuisance factors make that not symmetric in practice. One of them is that the lighting is not symmetric. So lighting typically comes from one side of your face, not from the other, okay? So when you do this flipping, that is going to introduce an artifact that will not allow your reconstruction to be correct when you do this, when you flip the switch. So now to fix that, another thing we did was to model not just geometry, but also photometry. So what we do is we get another bit of a network that estimates the light source, and then we get a shading function, which is also based on that. So this has two benefits. One, fixes this issue that the illumination is not symmetric. The second thing that it does, it links up geometry, which is captured by the depth map, directly with illumination. So this is similar to shape from shading. Now, when we thought about this, initially we thought this is not going to work because these images are too noisy. And shape from shading usually works if you have clean data, but actually this turns out to be quite effective, okay? Because it links up directly the shape to the photometry. And then if you do that, what you learn here is not a texture anymore, it's an albedo. So the illumination has been removed. You get a canonical view here, and then the renderer, the code of the renderer is to deform that in such a way that you get the correct viewpoint as well, okay? Final ingredient, and then I'm gonna finish with that. If you think about it, it's still not enough because face is not symmetric. For example, in this case, the hair is not. So what's going to happen is that when you flip your texture or your albedo, then that's also going to create an artifact. And to be able to detect those, we do one last thing. So we produce a confidence function that for each pixel, for the straight image and for the flipped image, is going to tell you, or the network is going to try to tell you how likely it believes that the construction is going to be accurate for that particular point. This is why we call this probabilistically symmetric, because we allow each pixel to be symmetric with a given probability, okay? And the network is going to produce that automatically, and this is self-calibrated because the sigma value we get here for each pixel is really the variance of a Gaussian that when you put in the loss function, and becomes basically a log likelihood that you optimize, and that gives you self-calibration for sigma as well. So this is actually does not make your loss training configuration more complicated. The loss is still very simple, okay? And this is really the combination of these ideas that make this work well, all right? So these are examples. Okay, so here you see what I meant. So in this case, when the switch is turned to 1, the network knows that this part will not likely to be reconstructed well because it sees that the hair are likely not to be symmetric, all right? Or they are not symmetric in this image. Okay, these are example reconstructions that we get. And you see here that, again, these have been trained without any supervision, just to give a data set of faces, and the reconstruction are fairly convincing. They capture really well, for example, the expression. But once you have trained a network like that, that generalizes. So now you can take that something which is not physically plausible, like a painting, and you can still get pretty reasonable reconstructions out of that, okay? And you can really take this to an extreme. So you can take something like a Picasso here, and then your network that was trained on real faces can still try to do some sort of 3D reconstruction, which tries really to fit that face, okay? So this generalizes really, really well. And you can see here another example of this emoji, which you get sort of creepy mix between a real face and what you actually see in the image, which is basically a ball, all right? And if you play this with videos, well, the reconstruction, they look pretty smooth, and but there is no temporal smoothing here. This is done on image basis. It just means that the reconstruction are fairly stable, even if you deform your face. And because there is no 3D supervision that you require, you can take any data set. So for faces, human faces, you can get better results using 3D supervision. But if you don't have those, then you, for example, cat faces, you can reconstruct them as well. And here you see that we can learn the axis of symmetry, because that's what the model is able to capture, as well as a map that tells you which part of your face are symmetric, which ones aren't. All right, so that's all I wanted to say. I realized that I'm sliding over time. So to cut it short, what I believe is going to be a very interesting area of research is learning geometry, or both in general object categories and classes and all these things that are semantically meaningful to a human. That's supervision. That's going to be at least definitely my agenda of research for the next couple of years. There are many challenges which are unsolved. One I think which is very, very difficult is to take this data and come up automatically with a breakdown on images into individual objects. So that's an interesting thing to look at, I believe. There's a lot of context I would like to discuss. There is no time to do it. Just one warning. I'm starting to notice that there's a lot of activity in ethics and GDPR especially, and how that's going to impact our ability in the community to use datasets such as ImageNet, which are fundamental for research right now. I'm not sure what's going to happen in the future, but it may be that as a community, we need to start to look into this more seriously and to develop datasets that are going to be better for people, but also better for us in the sense that we actually are to use them a year from now, and we don't stop doing research. Okay, so thank you. And if you have questions, I'm more than happy to answer them.
Thank you, Andrea, for this wonderful presentation and this great overview over a lot of amazing research. Do we have questions? If you do have a question, please switch on your camera and microphone and just ask, or you can put the Q in the chat if you want. Maybe I'll start with a question myself. You started your presentation with this framework of contrastive learning, and you distinguish invariance and discrimination. I think in many, human vision challenges, there's something in between that I would call not invariance, but maybe robustness. For example, humans would recognize things as a car, even if it's slightly rotated, but if it's completely like 180-degree rotated, you would not immediately recognize it as a car, because it doesn't typically arise upside down. How would you do that? Because it's not really pulling things together or pushing them apart, but it's a little bit both, depending on the amount of transformation.
Yes. Well, you can do that in different ways. One would be to predict the degree of transformation that exists between two data points, or even which transformation exists. And people have been doing that. In practice, what happens in the current formulation is that the transformations are not necessarily excessive. They are pretty brutal sometimes, to be honest. Okay, but typically 180 degrees rotation is not used, which is probably related to what you just said. So we have, as humans, a strong bias that we live upright, so probably we do not develop a strong ability to recognize things where they're upside down. I guess if we live, so if we were born on a space station, maybe that would be different to some extent. But because we have gravity, then yeah, we have this bias and we use it for recognition. And in fact, when we choose this transformation for contrastive learning, we do not have complete rotations. You could also try to, so you can bound the amount of transformation that exists by bounding those transformations in the first place. And if they are too large, you can maybe just ignore them. Say you can say this is neither a positive case nor a negative case. So instead of trying to push together or pull it apart, I'm just gonna leave it there and just ignore it, right? So there are all these different things you can do. In my view, the whole story about contrastive learning is too simplified. When you learn a presentation, that should be good for many different tasks, not just classification. Should be good for 2D, reconstruction, key point detection, etc., etc. And so what happens in practice is that you have a representation, which is a trunkier learning, and on top of that, there are a couple more layers that do actually the classification or the contrastive task. But the representation you learn, the real thing that you really want, is much more generic than just solving that contrastive task. That's just a pseudo task, if you like, just as an excuse for learning something. But the representation should be more able to capture more information than just distinguishing a class from another, right? So, and how to do that optimally, I think, is still a research question. Okay, but yeah, as I said, just invariance and this sensitivity, that does not exhaust what the representation should be doing. It's just a simplified discussion, really.
All right, thank you. There is a question from YouTube. Saravan Kumar is asking, is it possible to identify pose of birds, low resolution 50 by 50 images, by learning the representation and its geometry, like key points?
Good question. This is actually something we're working on right now. I don't have an answer yet. Hopefully in a month, yes. For now, it's still a bit challenging, yes. There are lots of work that do reconstruct birds in 2D with little supervision, only 2D supervision, but they typically use either a shape model, which tells you the bird shape is like a pear, basically, and you need to at least know that. It's weak information, but you need to have it. Or maybe you need to have a method that can segment out the silhouette of your bird. Okay, and but if you don't even have that and just have, say, videos, and you want to learn from scratch from those, or just maybe even still images, I think this is still a little bit harder than what we can do, but maybe is within maybe 6 months to a year of research, I would say.
Right.
I have one question actually.
Yeah.
So first of all, like, super cool work. It's really exciting. I mean, all the self-supervision. I think that's obviously very important for many tasks and many downstream tasks. So I really like the last paper when you're doing the 3D reconstruction of the faces. So I mean, it seems, right, basically you're doing multi-view reconstruction, but the multi-view constraints are now coming across samples and not just from one specific face. And it's very exciting that this is working. And it seems the key is you have to basically constrain the network enough that it can like cheat and like just predict a flat plane by introducing things like symmetry constraints. So what do you think is the path forward to, I don't know, like generalize that in a sense, like not have one specific symmetry constraint, but figure it out from the data through some clustering or whatever? I feel that that's a really cool avenue, right?
Yes, I mean, I can tell you about one work I've seen recently, I believe in Unclear, which goes beyond what we did. Sticks from what we did, but it generalizes it exactly by removing this constraint of the symmetry. So what I've done is and I'm hesitant to talk about it because I don't necessarily like guns too much, because they're tricky to train. But admittedly, this was a cool piece of work. So what they do is they train a gun to learn sort of the manifold of possible faces. Then they take a face image, they pretend is an ellipsoid, rotate a little bit, and then they feed that into a GAN to refine it to an actual face, and they pretend that's a different viewpoint of the same face, and that works. Okay, and that doesn't require any symmetry because you can do that with buildings, and they showed it works as well. So that's a different. So in other words, a generative model like a GAN can potentially learn to generate multiple views automatically, and if that's true, then effectively it means that implicitly the GAN has learned 3D geometry in a way. I'm a bit hesitant to say that because that's like a strong statement, but it seems that you can actually pull out this information from a GAN, and I think so. Then again, this basically learns multiple views without only having a single sample at a time by learning a statistical model on this manifold of images, if you like. Okay, so even manifold is not a appropriate name for that, but so this sort of space of images, or distribution of images.
I guess I could ask the same question also for motion constraints, right? I mean, I would really love to see that if you could animate the face later and you wouldn't train it just on one image, but rather on a whole sequence, right? And you can animate it. Shouldn't that give you also additional constraints? Because at least you see the same face. You know the identity is the same across frames, right?
Yes, absolutely right. So in fact, my focus right now is learning from videos, because I mean, we have videos. They are not any less abundant of images, I guess. Maybe they are a little, but for all practical purposes, we have them. And they can simplify learning these things a lot, I think. So that's what we're looking at the moment. When you do, for example, a reconstruction for motion, you can constrain your shape to follow a deformation which is physically plausible if you have a video, something you cannot do if you only have still images. And people have been doing that as a formal regularization or constraint for reconstruction for motion forever, really. So this is nothing really new. Another thing which is nice about geometry is that links back deep learning, what we're doing 25 years ago when it started, but maybe 20 years ago. So
yeah, no, but I think that's really cool. I don't know. I would be very excited to see that, like, the people explicitly using like physics priors in a sense as constraints throughout the video, like how objects move, how things prograde, right? Like, and I think that would be fantastic, right? It would be good news because this seems like a lot. It seems pretty generalizable to cross a lot of different objects, I think. And I don't know. It's not. I mean, I don't know. Like, that's why I like your paper. You were one of the first that did this for 3D already, from across the samples. But I think for videos, it's there's not a lot of work there right now.
No, it's true. Videos, one issue with videos is that they are expensive to work with. So it's actually I would say something that a company would have an easier time to do. Those companies anyway, like Facebook, for example. But actually, we're trying to do this also in Oxford. This work was done in Oxford, by the way, the last one. So you don't need those resources to actually work in this field. But yeah, videos, I think one reason why videos are not being looked at as much is just because they are more computationally intensive. But I do believe they are easier, actually, so statistically at least. So it's worth looking into that for sure.
Cool, thanks.
Do we have any other questions?
Yeah, I have a question. First of all, thanks for the talk. It was amazing that you covered so many topics. So my question is, with the last work with the face, how have you considered apply a constraint to the shading part? So because to impose it's a plausible physical model. So you don't the energy conservation, for example.
No, it's not as complicated as that. It's a simple inversion model, really. So what it means is you get normal from your depth map by taking a numerical derivative, a very simple thing, and then you cross product. So you dot product with the light direction, and that gives you an intensity value. That's it, really. So it's still a simplified model, but that's another message I wanted to convey here. So in vision, we have lost geometry a little bit because of deep learning or machine learning in general. And we're not modeling things in a very detailed manner anymore. We just offload everything to networks. There is a question of whether modeling these details is actually useful, and this is an example where it is. So even something as subtle as shading, which you think is too fragile to explain an object category, maybe it's not all that fragile after all, so it can be useful.
Can I follow up here, Andrea? This intrigued me. You mentioned it yourself, shade from shading is a classic in computer vision, but at some point it was decided this was a dead end, and people said it only works in the studio under very controlled illumination, etc., and it doesn't work out in the wild. This was like a consensus at least a few years back. Now you're kind of revisiting shape from shading, and to me it seems that most of the geometric details come through the shading modeling. Why does it work here if it didn't work in the past? What's different?
What's different? Okay, so my 2 cents maybe is that it is a noisy signal, but if you average that over 100,000 different phases, and there is a network in between that can learn from this noisy information, then you're successful. Before, in a classical computer vision, we were trying to get one reconstruction from maybe 1 or 2 images, and that was that. And then you cannot go against the noise. But here you get a little bit of information from the shading, which may be very noisy, but you consistently get it. And the network learns to integrate that information over a large data set. And I think the combination of these two things make it work.
So in some sense, it's because the geometry doesn't arise through solving a PDE, but it comes through a deep network. That is okay. Yeah.
Yes, and the key is that the deep network really shares information between all these different examples, not just one at a time. But again, that's an hypothesis. I don't have any proof that this is actually the case.
No, it's pretty plausible. Any other questions?
Sorry, but I would like to know that so in this case you use the symmetry and it was quite successful, like a property.
Yeah.
But somehow it was because the symmetry was not so complicated to impose. But what about if you want to impose some a physical a property from the world? Do you think that it would be possible to do it kind of like in a way that is not too detailed?
Well, there are many properties you might want to impose. For example, we have been working on human reconstructions, which is a lot harder than this, by the way. And we're trying to impose the fact that there's a skeleton inside the human, right? And learn out automatically. So that's another kind of constraint you want to impose. I've been slightly cheating here in the sense that in this case, the object itself is in each instance symmetric, but if a human is symmetric, right? Because the structure of a human is symmetric, but not the instantiation of a human pose. Most poses just you strike, they're not symmetric. Okay, so there is a difference between having a category, which is a symmetrical level of the structure, and something which is a symmetrical level of individual instances. So that's another example of symmetry, which is more general than this one. Okay, and that's a lot harder to impose. So the answer is it's more fragile. We don't know how to do that well yet, but it's definitely something to look at. Okay.
Yeah, it is very interesting. Thank you.
Any other questions? Okay, if
Excellent.
not, I think then thank you again, Andrea, for the wonderful presentation and the great work that you've shown here. It's really amazing. And thanks everyone for joining and for the lively Q&A. Thank you so much.
Bye-bye.
Bye-bye.
Actually, I should stick around, right? I think.
I guess, Matthias, are you stopping the live stream now? Maybe Matthias.
I've ended